Welcome to CSC 201, Lesson 7.2, One-to-one, onto, and inverse functions. A one-to-one function is a function where each element of the codomain is an image of at most one element of the domain. So an example of a one-to-one function, we have any two distinct elements of X are sent to two distinct elements of F, one-to-one. A one-to-one correspondence. An example of a function that's not one-to-one, sometimes it's helpful to think of these kinds of functions as many-to-one. So here you have x1 and x2 both being sent to the same y value. So f of x1 and f of x2 are the same y value. Okay, so looking at some arrow diagrams here, are either of these one-to-one? So let's see. A gets sent to one thing. Okay, any elements from X, do any of these elements get sent to the same Y? So look at my Y's. None of them have arrows coming from two different values of the domain. Okay, so this is one-to-one. Whereas this second one, W is a problem, right? W has arrows coming from two different elements of the domain, which means 2-to-1, right? Two X's going to one Y. So this is 2-to-1, and this is not one-to-one. So the formal definition of one-to-one, a function f from x to y is one-to-one, also known as injective. If and only if, for all elements x1 and x2 and x, if f of x1 equals f of x2, then x1 has to equal x2. Okay, so if we look at this many-to-one function, here I have f of x1 equaling f of x2. That's the if part. But x1 and x2 are different, right? x1 does not equal x2. So in order for two y's to be the same, they have to have come from the same x. That's what this says. So let's define a function f from the reals to the reals such that f of x equals 3x plus 5 for all x in R. Is f one-to-one? Prove or give a counterexample. So we're going to use the definition to prove it. We're going to suppose f of x1 equals f of x2, and we're going to show that x1 equals x2. Suppose f of x1 equals f of x2. We need to show x1 equals x2. Okay, so if f of x1 equals f of x2, that means the function f of x equals 3x plus 5. So that means 3x1 plus 5 equals 3x2 plus 5. We can subtract 5 from both sides, and the equation will still be true. So we have 3x1 equals 3x2. Divide both sides by 3, and the equation will still be true. And I'm running out of room here, sorry. So x1 equals x2. So we showed x1 equals x2. Okay, here's another function, f, going from the reals to the reals. We're going to define it as f of x equals x squared. Is f one-to-one? Prove or give a counterexample. So this is not one-to-one. It is many-to-one because there are two x's that will go to the same y. Consider f of 2 and f of negative 2. Right? F of 2 is 4, f of negative 2 is also 4. So if I have an arrow diagram, from the reals to the reals, I have a negative 2 and a 2 that both go to 4. So you've got 2 to 1, right? 2 going to 1 and not 1 going to 1. So this is not 1 to 1. Okay, another definition. A function maps onto its codomain if every element of its domain is the image of some element. Sorry, I read it wrong. If every element of its codomain is the image of some element of the domain. So this type of function is called onto, or sometimes also surjective. When a function is onto, its range equals its codomain. That's what it means. So every element of its codomain got mapped from something. So here's an example of onto. So I have 4 elements in the codomain. They all have arrows being drawn to them, right? So the domain, the function f maps onto its codomain. Every element in y equals f of x for at least one x in x. Now here's an example that's not onto. I have a couple of lonely dots here in the codomain that are not images of anything from the domain. There are no arrows drawn to them. So this function f is not onto. So let's look at a couple of examples here. And this first one, and we have a lonely b, that means that this is not onto, right? Every element in the codomain needs to have an arrow drawn to it to be onto. Now this one, every element in my codomain has an arrow drawn to it, so it is onto. So the formal definition of onto is a function f that goes from x to y is onto if and only if for every y in the codomain there is an x in the domain such that f of x equals y. Define a function f from the reals to the reals such that f of x equals 3x plus 5 for all x in R. Is f onto? Prove or give a counterexample. Okay, so just quickly thinking about the graph of f of x equals 3x plus 5. Looks something like that. Okay. So it looks like its range is all real numbers, right? The smallest, this goes down forever and this goes up forever. So the range is all reals, which means that the range equals the codomain, which means this is onto. But a more formal proof would use the definition, the formal definition. So I need to let y be an element of the reals, an element of the codomain, such that y equals 3x plus 5, right? I have to show that there is an x that can make this work. There is an x that you can plug in to 3x plus 5 to get any y in the reals. Solving for x yields x equals y minus 5 over 3. Therefore, y is equal to f of x, which is equal to f of y minus 5 over 3. So for any y, right, for any y, you can find an x by doing y minus 5 over 3 that will give you that y as an image. So there exists an x, which you calculate by doing y minus 5 over 3 in the reals, such that f of x equals y. So yes, this is onto. Okay, so here's an example of one that's not onto. Let's see if we can figure out why. Here, f goes from the integers to the integers. So this is almost exactly the same, right? Here, I had f going from the reals to the reals, f of x equals 3x plus 5. Here, I have f going from the integers to the integers, and f of n equals 3n plus 5. It's like the same function formula, but the difference is that I can only input integers and output integers. Is f... Ooh, this is supposed to say onto. Okay, prove or give a counterexample. So, consider f of n equals 6, right? So if 6 is my output, I have to figure out an input that would map to 6 in order for this to be onto, because it has to be true for every possible output that you can find an input that maps to it. So if f of n equals 6, then 3n plus 5 equals 6. And thus n would have to equal 1/3. So 1/3 is what you would have to plug into the function f in order to get an output of 6, but 1/3 is not an element of the domain, right? Because the domain is integers. Okay. Since 1/3 is not an integer, there does not exist an n in the integers such that f of n equals 6. So this tells me that it is not onto. You only need one counterexample to show that it's not onto. One output that does not have an arrow mapping to it from the domain. Okay, 15, putting the two definitions together. A one-to-one correspondence, also known as a bijection, from a set x to a set y, is a function that is both one-to-one and onto. So we have a one-to-one mapping, meaning not many to one, but there are no arrows pointing to the same y value, and every y value has an arrow pointing to it. So a one-to-one correspondence, right? So you can see what that means is that each x lines up with one y. Every x lines up with every y. So a bijection is reversible. That is, if f going from x to y is both one-to-one and onto, then there is a function from y to x that undoes the action of f, and we call it f inverse. So if f goes from x to y as a bijection, then there is a function f inverse that goes from y to x, defined as follows. So f inverse of y equals x if and only if f of x equals y. So it's just a reverse trip. Okay, so if we have x and y, f takes an input from x and maps it to y, and then f inverse brings it back. Okay, the function f from the reals to the reals, defined by f of x equals 3x plus 5, has already been shown to be one-to-one and onto. We did that earlier. Find its inverse function. So this is something you've probably done in a previous math class, finding an inverse function. So we need to reverse it, right? We need to know if y equals 3x plus 5, right? So you have x's that you plug in and you get y's. I need the reverse formula where if I give you the y, you can go backwards and tell me the x that it came from. So we do this by just solving for x. So we subtract 5, and I have y minus 5 equals 3x. And then divide by 3, and we get x equals y minus 5 over 3. Now, typically, functions use x as their input and y as their output, right? So my original function was f of x equals 3x plus 5. And it's just, that's just a convention, right? That x is the input and y is the output. So when you write it like this, your function, it's good at conveying that this is an inverse, right? So y is now your input and x is now your output because you're going backwards from the codomain to the domain, right? But it's not written the way we conventionally write functions where x is an input and y is an output. So it really depends on the context and what a question on a homework or test is. How they ask you to write your answer. This might be just fine. You might also want to write it as f inverse of y equals y minus 5 over 3, right? Or sometimes you swap the name of the variables, right? Because it's weird to write y as an input. Y is typically an output. So here I'm just going to rename the variable. Instead of y, we rename it x, so that we would write f inverse of x equals x minus 5 over 3. So these are just two ways of answering the same question, of finding an inverse function f. This one uses the conventional x is an input, right? This one, it makes it clear that this is an inverse function because it's using y as the input, meaning it used to be an output. So this one has its advantage, and then it's like reiterating that this is an inverse, that y, it's using y as the input because y was the output from their function f. This one has an advantage in that you can graph f and f inverse on the same xy plane, right? Because x is your input and y is your output. So you can graph f and f inverse together if you were interested in seeing them on the same plane.